Okay, so now we're starting chapter 16.1 with an idea called line integrals of functions. And so we're going to start just by talking about the definition of what line integrals are, and then I'm going to draw a couple comparisons to Calculus 1 and how this relates to Calculus 3, like where we're going with this idea. So the definition of a line integral is an integral where the function to be integrated is evaluated along a curve instead of an interval. So we're used to in Calculus 1, let me draw a little picture. So in Calculus 1, we were used to the idea of integration taking place over an interval on the x-axis. Right, so you would evaluate your function. Well, let me draw a better function. From A to B. So the interval of evaluation was an interval on the x-axis, and that's inherently a linear idea. So this whole concept in Calculus 1 was a linear one-dimensional, a 1D axis of integration. Right, so we were limited to just integrating across one axis. But now that we're in Calculus 3 and we're doing things in multivariable, right? We have functions of two variables, surfaces in 3D, we need to expand this idea to talking about things in higher dimensions. So the equivalent in Calculus 3 is going to be that we can integrate along any path. So not just limited to a one-dimensional interval of integration, but we can integrate along a curved path. So let's draw what that would look like. So I'm going to draw my 3D axis here. And so what I'm going to do is I'm going to assume that the curve C that we're integrating over, right? So the curve of integration, right? I'll draw that here in green. I'm going to say that that's just some generic curve on the xy plane. Now, note that it doesn't have to be limited to the xy plane. The curve C could be in 3D and extend in all three dimensions, right? But just for drawing an example, it's easiest to visualize if I just limit the curve to being in the xy plane for now. So let me draw an example. Here's like a curve C, right? There's just a generic path of integration, right? That could live in the xy plane. And now, let me draw our function. Right? So the function is going to be of two variables. Right? So this is f of xy. Right? And it's a surface in 3D. And so that's going to live up here. Right? So that's some surface, and that defines the height. And so what a line integral gives you is it's the area between your function f and a curved path of integration. So let's just say that the height at each of these given points, right? So evaluated here, maybe the function has a value there. Maybe it's like this, where it kind of just comes down. So these are all the evaluation points along the curve. And if you were to trace that out, that would give you, right, something that kind of looks like this. So now you're finding the area between the curve and the path of integration. But now we're not just limited to integrating over a one-dimensional axis, but our path of integration can actually move around and be 2D or 3D. And so we're still finding area under the curve, but now the curve can actually be curvy. Right? So let's get what that area is going to look like. It'll look something like this. So this is the value of what we're finding, right? So it's this area right here. So what I like to think of is it's kind of like the area of the fence, or a fence that traces out the curve C, where the top of the fence is defined by the function value f of xy at every given point. So we're finding, so a line integral, let me just write this out for formality's sake. A line integral gives the area under a curve, under a function, under a function over any curve C, right? And so I think what's even better than just a verbal explanation is I think you would get a lot out of watching an animation. So I have a really cool animation pulled up. So let's watch it together. So here is like a contour plot of a function f. So this is the function that lives in 3D, but these are like the level curves. And here is C. So our C is from A to B, right? So that's the curve we're integrating across. And now you can see how the function value is defined at every point on the curve C. And now if we just stretch that out and kind of flatten it so we can look at it on a plane, you can see how the function value changes if we just stretch out C to be flat. And now you're finding the area. And this is the formula that we're going to explore here in a second. So we'll see that that is the actual formula for evaluating a line integral. Let me go back to our notes. So here's the second important note, is that a curve C, so this is the curve that we were evaluating across, is the path of integration. And it is given by a parameterized function of t. So if you remember from chapter 13, we spent a lot of time writing parametric functions, right? So it's like vector valued functions in terms of t that can give you any point in space. So we typically will write C. So the curve is written in this form. Typically as a curve R of some t equals some function of t in the I direction plus some function of t in the j direction. And then our curve, like I said, doesn't have to be limited to 2D. It could be a three-dimensional curve. And in that case, it would also have some function of t in the k direction. Right, so this is just the path of integration, has nothing to do with the function. Right, so those are two separate ideas. So we're just talking about the path of integration. So we're also going to spend some time in this video talking about how you find and write this curve C to integrate over. So let's get to the formal definition of the formula for how you actually evaluate one of these. And so we know that in general, we're doing an integral. So an integral over a curve C, so instead of an interval, of a function that can be up to 3 variables, or it can actually be more, but we're going to write it like this, right? Z, and then this ds here, we're not going to use it, but that's just like the arc length differential. That's the arc length differential. And what ds means is it's tiny little segments of a curved path. So these little segments are ds. Just like little segments along the x-axis are dx. Right? So that's ds is little segments of a curved path. So it's the arc length differential. And so that's not super useful because we don't know how to evaluate things in the form ds. But that line integral over a curve of a function, the actual usable form of that is going to be an integral of a function written in terms of your curve C, so in terms of r of t, times the absolute value of the velocity function, right? So the first derivative of your curve, dt from A to B, right, where C, your curve that you're integrating across, is r of t. So what this means is that the function you're integrating, this function, cannot be written in terms of x, y, and z if you're integrating with respect to t, right? The variable you're integrating needs to match up with the differential at the end. So you need to plug in your equation for r, right, the x, the y, and the z values, into your function, write it in terms of the curve you're integrating, right? So it's just values of t, and then multiply by the absolute value, or the magnitude of the first derivative of your curve, right? And then bound a to b, where r of t needs to be bounded from a to b as well. So let me add that up here, where t goes from a to b. And those will become the bounds of your integral. And I think it'll make a little bit more sense if we do some practice in writing parametric functions for different curves. But this is the actual usable form that we'll use for evaluating line integrals. Oops. I won't box it. That's going to be hard. But yeah, so that is the usable form. Now, as another note, when we parameterize a curve C, it has to be smoothly parameterized. So we have to find some way to smoothly connect the curve that we're integrating across. So as an example, something we could not parameterize. All right, so we couldn't parameterize this curve. So let's say that the C we're given looks like this. So here's C, and then that. So it comes out and then up. So if this is C, C cannot, in this case, cannot be written as one parametric function, right? Because it's not smoothly connected. But what we can do is use the property that line integrals are additive. So what we can do instead is break this up into two different curves and integrate the first one and then add the second one. So what we can do instead is break this up into C1 and write a parameterization for that first segment, and then break it up and write a parameterization for the second segment, and then the line integral across the entire thing will become first the line integral of C1 of your function written in terms of like R1 of t, right? So your first parametric function times this dt plus, right, so that took care of the first curve along the xy plane, and then to get that second part, we can just add in the line integral over the second part of that curve. So we'll do the function, now we just evaluate it on the second curve, right, times the magnitude of the velocity function, or of the first derivative of the curve, dt. Right, so if the curve that we need to integrate, the path of integration, is not smoothly connected, then we can use the additive property to break it up. So that's the idea we're talking about here. So yeah, so if C cannot be written as a single smoothly connected parameterized function. So that's when we would use that. Okay, so let's jump into just practicing writing some parameterizations of C for different paths. So all we're doing in this example one is looking at how the heck do we construct this equation from some different paths. And so we're going to be given a geometric drawing of the path, and we need to construct the parametric function that we can use to integrate. So we don't have any function, we're not going to evaluate any line integrals, we're just finding the curve equation. So let's start with the first one. And as a note in this class, there are going to be curves that you know how to parameterize. So they're going to be line segments or functions like parent functions that we know, or pieces of circles, right? Those are all general shapes that we know how to write parameterizations for. So let's do some examples. So number one, so what it means to parameterize something is just to write it in terms of t. So we need to have only t be the variable. So we need to write an equation like r of t equals something that will trace out this line segment from -1 to 1. So if we notice, it's only on the x-axis. It only has an x component to it. So in this case, it is just going to be t in the I direction, right? Because we can say that the t value corresponds directly to the x value. And then we need to bound it from a to b, right? Like we said up here, your curve needs to have t bounds, so you know what segment of that curve to get. And so in this case, t will go from, you can guess, -1 to 1. Right, so where t goes from -1 to 1. let me rewrite that in the middle, just so it's a little nicer, where t goes from -1 to 1. And so you can imagine if you plug in -1 for t into our R equation, that will give us -1. And if you plug in, say, t equals 0, that gives us 0i. And if you plug in 1, you get 1i, which is here. And all the values in between will trace out that curve. So that could be our curve of integration. So that's how we would write the first parametric function. Now let's look at b. So b is a curve on the yz plane, and we can write an equation for this. This looks like, let's see. So it looks like the equation, so if I were to write out the equation for this line just in rectangular coordinates, this looks like z equals 2 minus 2y. Right, so if you plug in 0 for y, you get 2, and if you plug in 1 for y, you get 0. Yeah, so that's the line z equals 2 minus 2y. So we need to turn this equation into a parametric form, right? So we need to just write it in terms of t. So let's get our R of t equation. And so we'll pick our independent variable y to just be t. And then we'll plug that in to the equation. So we can say let y equal t, and then in that case, z will equal 2 minus 2t. So these two equations together are now written just in terms of t. So we're going to have 0 I components, right, because there's nothing in the x direction, plus our y component is t, so that's going to be t in the j direction, plus the quantity 2 minus 2t in the k direction. Right, so this is how we parameterized that function just in terms of t, right, using that equation. Okay, let's do number 3. So number 3, this looks like the unit circle. Well, it's not quite the unit circle, it's just a circle centered at the origin with radius 2. And so we know from chapter 13 that our parameterization for any circle is that cosine I plus sine j. That gives us the unit circle on the xy plane. And now we just know that it needs to be a radius 2, so we're going to multiply by a 2 factor out front. So this one's going to be pretty easy. So that's just, right, our curve of integration will just be cosine t I plus sine, it's actually 2 cosine ti plus 2 sine t j. All right, so that gives us a circle centered at the origin with a radius 2. And if we want to just rotate around it once, then t will go from 0 to 2 pi. Right, so that will give us one full rotation around that curve. Right, so we're integrating around it once. Oops, I actually forgot to bound this one. Right, so we need to write t-bounds as well. That's important. So in this case, what does t go between? So t starts at 0, because plugging in 0 for t will give you just 2k. So it starts at 0, and it looks like it goes until t equals 1. Right? Because if you plug in 1, you get 1y, and then you should have 0k. Yeah, so it's t equals 0 to 1. Okay, so those are our bounds there. Our bounds on number 3 were 0 to 2 pi. And now let's do the very last one. So this looks like another segment of a circle centered at the origin with a radius of 2, but we only want 1/2 of it. Okay, so this is going to be just kind of like a transformation of the last one. But if we notice as well, this curve is actually on the xz plane, not on the xy plane. So the two components we have are not going to be I and j, but to get it on the xz plane, you need I and k with a 0 y component. So instead, this function is going to be written in terms of i's and k's. So let's try this one. So R of t is going to be, right, we need a radius of 2, so it's going to be 2 cosine t I plus 2 sine t k. right? So that will give us the circle center of the origin with radius 2 on the xz plane. But we actually only want half of it. We don't want a full rotation of the circle, so we're going to bound it, right? So we only want the portion of the circle where t goes from 0 to pi, right? So that's half of one full rotation. That will give us just that upper half of the circle. So that's different ways we could parameterize different paths of integration, and then we would use that path to plug in right to here. So we would rewrite the function in terms of that parameterization, take the magnitude of the first derivative of the parameterization, right? We practice finding the bounds a to b, and so that's how we would evaluate a line integral over these different paths. So let's do a full-fledged example. So this is the first real worked out problem. So number 9. So we're going to evaluate this function. Let me get some highlighter. So here's the function we're going to integrate. Right, so that's our f. And the c, the curve we're going to integrate over, is a straight line segment, x equals t, y equals 1 minus t, and z equals 0. So this was actually written out for you. So we can actually translate that into a parameterized equation really nicely, right? Where the x component is just t, so t in the I direction, plus, 1 minus t in the j direction, and then 0k, from 0, 1, 0 to 1, 0, 0. So this information here, this tells us about the bounds a to b. So this is telling you what portion of that curve you want. So this tells us about a to b, right? And so if we want it to start at 0, 1, 0, what value of t gives us that? Well, that's actually going to be t equals 0. So from 0 to, and now we want 1, 0, 0, that would be 1. If you plug in 1, you would get the point 1, 0, 0. So that's 0 to 1. So we have our parameterization. We have our bounds as well from a to b. Now, what else do we need to do? So let's just actually start writing the integral out, and we'll fill in the pieces that we need. So we know that the general form is going to be the integral from a to b of our function written in terms of our curve times the magnitude of the first derivative dt. So let's see, what pieces do we have so far? So we found our bounds a to b, that's from 0 to 1. We know what our r of t function is. We can plug in pretty easily this r of t into our function f x of x and y. So we're just going to plug in t for x, and we're going to plug in 1 minus t for y. So that's pretty easy to do. And then we just need to calculate the first derivative and then take its magnitude. So we can do that next, and then we'll just evaluate the integral. So let me move this down real quick. Oops. So I think the next thing I'm going to do is I'm going to work on finding this magnitude of the first derivative. So here's r of t. So in this case, we'll find v of t, where v of t is going to be, that'll be 1i minus 1j, right? And then we'll take the magnitude of that. So the magnitude of v, that will be the square root of the sum of the squares. So it'll be the square root of 1 squared plus 1 squared, which is the square root of 2. So that's, right, that's what we plug in here. So we have the square root of 2. And now let's just evaluate our function. So let's our function, which was, in this case, x plus y. Let's write that in terms of our parameterization to get it in terms of t. So in this case, for x, we're going to plug in t, and then plus y, which is 1 minus t. So plus 1 minus t, which in this case just equals 1. So that's pretty easy. The function we're integrating in terms of the parameterized curve is just 1. So now we have all the pieces in place. This is kind of like a cooking show now, where you have all the measured out pieces placed in front of you. Now we just got to combine them together into this general formula. So now let's write the specific integral for this problem. So now we have all of our pieces. So in this case, we're going to get the integral from, what were our bounds? 0 to 1, where our function evaluated in terms of the parameter is just 1, right? So 1 is our function times the magnitude of the first derivative of the curve, which in this case is the square root of 2 dt. So that's pretty easy. So we can evaluate that. That's just going to be the square root of 2t evaluated from 0 to 1, which is just the square root of 2. All right, so that's how we integrated this function over, we integrated this function over this curve that it gave us. Okay, sweet. So it's not too bad, actually. Let's try number 12. So number 12 is having us evaluate this function. So here, in this case, that's our function. All right, so that's the part that lives in 3D. It's some surface. And now, again, the curve was already given to us, right? Oh, even better. So the curve and the bounds are already given to us. So here's the curve, and here are the bounds. Right, so we're going from negative 2 pi to 2 pi. So I'm not even going to worry about drawing this out. We don't need to have a sketch. We're just going to plug in the pieces and go. So I do know that we need r of t. All right, so we have that. Now I'm just going to calculate that first derivative. So let's get v of t, right? So we can plug that into the equation, because I know we're going to need that. So in this case, the first derivative of 4 cosine ti plus 4 sine tj plus 3tk is going to be, that'll be negative 4 sine, negative 4, how do I get rid of that? Negative 4 sine ti plus 4 cosine tj plus, I believe it's 3k. Plus 3k. So now let's take the magnitude of that. So the sum of the squares. So in this case, that's going to be the square root of the sum of the squares. So the square root of negative 4 sine t squared is going to be 16 sine squared of t plus 16 cosine squared of t. And you might already see where this is going and why this is not going to be as bad as it looks. Plus, and then 3 squared is 9. So in this case, what we can do is we can factor out a 16. We'll factor out a 16. So this is going to be the square root of 16 times, that'll give us sine squared plus cosine squared, which is just 1 plus 9. So that's the square root of 25, which equals 5. So the magnitude of the first derivative of the function is just 5. So that's pretty easy. So now the next thing we need to do is rewrite our function in terms of the parameterization. All right, so that's going to be plugging in r of t into f. All right, so it's the square root of the x component squared plus the y component squared, which is going to be the square root of, what's the x component is 4 cosine t, so that's squared, is going to be 16 cosine squared of t plus, and the y component was 4 sine t, so that's going to be 16 sine squared t. All right, so I need to extend that bracket a little bit. And then this is going to be the same thing. The Pythagorean identity is hiding in there. That's just going to be 16 times 1, which is the square root of 16, which is just 4. Whoops. So that just becomes 4. So now we have everything written out. We can plug it into our line integral. So our line integral, what were the bounds again? It was from negative 2 pi to 2 pi. So from negative 2 pi to 2 pi, where our function evaluated in terms of the parameter is 4. So it's negative 2 pi to 2 pi times 4. And what was the magnitude of the velocity? Was 5 dt. So now we can evaluate that pretty easily. That's just going to be 20 t evaluated from negative 2 pi to 2 pi, which becomes, so plug in 2 pi, you'll get 40t minus a negative, so that's plus 40t, so that's going to be 80 pi. There you go. So that's how you evaluate that line integral. So see, these aren't really too bad. It's really just understanding what's going on here, why we can integrate over a curved path, and finding the different pieces to evaluate. So this is our last number 22. Let's tackle it real quick. So this one is finding the line integral of this function. So here's our f of xy. So that's our surface in 3D that's defining the height that we're integrating along the curve. And this one's super easy. It gave you the curve as well. You're not always going to be given the curve. Sometimes you're going to have to construct it, just like we did up here. It might give you some information. You have to come up with R of t. But it looks like in a lot of these, it would just already gave you R of t straight out. So this is going to be pretty easy as well. So we have R of t. I'm just going to find V of t. So in this case, V of t is going to be negative sine t plus cosine t from 0 to 2 pi. And so the magnitude of V, the magnitude of the first derivative is just 1, right? Because that's going to be the square root of sine squared plus cosine squared. So the square root of 1 is 1. And then what else do I need to do? Oh, let me write the function in terms of r. So in that case, our function was x minus y plus 3. So that will turn into the x portion. So x is cosine t minus y, which is minus sine t, plus 3. So that's the new function we're integrating. So let's plop this all into our line integral formula. So it's the line integral from 0 to 2 pi, where our function is now, what is that, cosine t minus sine t plus 3. All of that times the magnitude of the first derivative, so times 1 dt. So we can evaluate that pretty easily. That's going to be the integral of cosine t will be, so that's sine t minus a plus cosine t plus 3t from 0 to 2 pi. And that will become, so you get 0, 1, 6. So I believe that becomes, oh yeah, minus 1. So it should be 6 pi. All right, so that's how you evaluate that. And just as an exercise, let's just try sketching out what that curve looks like real quick. Oh, actually, wait, we don't need to do that. It's really easy. Cosine ti plus sine tj from 0 to 2 pi, that's just your unit circle on the xy plane. So you're finding the height, right? So if we were to draw out a picture of what's going on here, 6 pi is equal to the height of this like circular fence. So here's C, right, where C is the unit circle, basically. And then I don't know exactly what the surface x minus y plus 3 looks like, but I'm just going to say it looks like some like plane that's kind of slanted like that. I have no idea if that's actually what it looks like. But in this case, 6 pi is equal to the height of a circular fence where the base, like the path of the fence is c, and the height is like, is defined by this surface. So let's just say it looks kind of like this. So there's the top. And so 6 pi is equal to this area here. So it's kind of like, whoop, that area and this area. Right? Where our curve of integration is c and the height is defined by f. So let me just write that out. So this, I don't know if this is actually what f looks like again. Oops, how do I redo that? There we go. Ooh. I love the functionality of the iPad. So this is f, right? But not really, because I'm not sure what it looks like. But if it looked like that plane, then 6 pi is equal to this area shaded here in yellow.